All right, getting started with class 2 carbonyls. Class 2 carbonyls are aldehydes and ketones. They mainly undergo addition reactions. But before we get into aldehydes and ketones, the first thing we're going to talk about them is reactions of organometallics with them. So naturally, we need to remind you what organometallics are, what they do. You've seen this slide at least 3 times by now. Carbon is typically an electrophile. There's typically a partially positive charge on a carbon because it's connected to an atom that's more electronegative than carbon. But carbon can be a nucleophile, and when carbon is connected to a metal, carbon is going to act as a nucleophile. Here are our favorite 2 examples of carbon acting as a nucleophile. If you have an alkyl halide and you add some solid magnesium to it, so sad we're missing that lab, adding solid magnesium to that guy, you're going to get the magnesium to squeeze between the carbon where the halogen was and the halogen. That's a Migber, that's a Grignard reagent. You do the same thing with solid metal lithium, you get that organolithium thing. That's old news of how to create organometallics, the 2 most common organometallics. Once you have an organometallic, more old news. How do they react? We'll draw this one. So here's that example. Grignards are strong bases, and when Grignards attack epoxides, old news, you attack the least substituted side, like that. I'm going to keep everything drawn in the same orientation in general, and I'm going to draw my Grignard thing that attacked pointed up because I'm going to say it's attacking from the top side while you're letting go of the oxygen on the bottom side. And I get this. And all of these Grignard reactions we're about to go through, they have to have some sort of acid workup later. It could be HCl, it could be sulfuric, it could just say H3O+, it could be all kinds of things, but they're all going to have some sort of acid workup later so that you can protonate that O- that you made, because Grignards are strong bases and OH can never exist in the presence of a Grignard because a Grignard will deprotonate that OH. That's a big deal. You talked about it way back when you were first introduced to Grignards. It's still a big deal now. So this is a Grignard reacting with an epoxide. Old news. When a Grignard reacts with an epoxide, you're going to do inversion at the carbon that got attacked. So this carbon gets inverted. Hopefully you know what that stereochemistry looks like. Should this methyl be dashed or wedged? Dashed, because I chose to point my benzene up. Was this carbon involved in the reaction whatsoever? No. Leave the stereochemistry alone. That center got inverted. That center was left alone. This center got inverted. This center was left alone. Yeah? Grignards with epoxides. Grignards are bases, and an epoxide in base attack the least substituted carbon. Done. There's our product, no stereochemistry. There's our product, no stereochemistry. If you drew it a different way, make sure your final products with stereochemistry match the right R's and S's of these. Just a really quick thing to note. Since we're reminding you of how Grignards react with epoxides, you probably need to remember how to make epoxides. One way is adding a peroxy acid to an alkene. Who's your favorite peroxy acid? Hopefully you have an answer there. The next example there is a halohydrin with a base. A halohydrin is an OH and a halogen on neighboring carbons. Remember, we made those guys back first semester organic. halohydrin, OH and a halogen on neighboring carbons. If you add a base like sodium hydride, you're going to deprotonate that OH, make an O-, and then intramolecular SN2. I'm not drawing out these because this really is just a reminder of old stuff, but it's worth your effort to try and draw it out probably. Let's synthesize a thing using a Grignard. Grignards can react with tons of things, and we're about to get into those other tons of things, but so far, all we know that Grignards react with are epoxides. So let's try to synthesize this guy using a Grignard and an epoxide. It's an 8-carbon alcohol, also known as octanol, and we're trying to make it from 6 carbons or less. 1, 2, 3, 4, 5, 6, 7, 8. So Grignards are very good at making carbon-carbon bonds. If you don't get anything else out of this material, you should know that Grignards are very good at making carbon-carbon bonds. Since I'm told this has to be made from a 6-carbon piece, I'm going to need to make this into 2 pieces, one that has 6 carbons, one that has 2 carbons. Well, an epoxide is a great way for 2 carbons to hook up with a Grignard. An epoxide can bring along more than 2 carbons, but an epoxide is a great way to bring along at least 2 carbons to the party. So I'm going to synthesize this from this 2-carbon epoxide and this 6-carbon Grignard. I'm going to add those 2 together, and I'm going to follow up with acid workup. Acid workup must be the second step, the follow-up step. Do an extraction something. 1, 2, 3, 4, 5, 6 carbons. You don't have to draw this part, but it would attack here and bust that open. Note that when your Grignard reacts with an epoxide, the alcohol that you make, every time a Grignard reacts with an epoxide, you make an alcohol. The alcohol that you make is a carbon away from, 1 carbon away from the carbon that actually got attacked. This carbon got attacked. This carbon has the alcohol. That's different for epoxides versus carbonyls that we're about to go through. Speaking of carbonyls, let's do them. You've seen this before. It's reminding you what a carbonyl is, but the reason I pulled it back in was to point out this. Class 1 derivatives do substitution, and class 2 do addition. Mostly. For now, they're going to do addition. What are the class 2 derivatives? That's aldehydes and ketones. Aldehydes are more reactive than ketones. Aldehydes are less reactive than anhydrides. And then ketones are more reactive than esters and carboxylic acids. So really, this slide is giving us a new setup for the corner of our paper functional groups. I'm going to draw it in 2 different colors here. I'm going to leave it small, but hopefully you're not too mad about it. Acid chlorides. Anhydrides. And that says aldehydes are less reactive than anhydrides, but aldehydes are more reactive than ketones. And as it turns out, ketones are more reactive than esters and carboxylic acids, which are more reactive than amides and nitriles. So carboxylic acids go over here, but I don't have any space right there. But you know how it works. So aldehydes and ketones now squeeze right between anhydrides and esters on our reactivity chart. Okay, cool. What's next? Aldehydes and ketones mostly do addition reactions. So I feel somewhat confident that you can draw this reaction without me ever drawing it, but I'll draw it anyway. Grignards can react with aldehydes. This is an acetylenic Grignard, but that doesn't matter. We don't care. It's any old Grignard. Grignards are strong bases. They're good nucleophiles. Attack the carbonyl carbon. In some of that other stuff we did previously, we made the carbonyl carbon. The carbonyl carbon had to get protonated first, but not here. Grignards are strong bases. Thou shalt not protonate the carbonyl carbon first when there's a Grignard around. Attack straight out of the gate to get this. And all of these reactions will have some sort of acid workup, an extraction of some sort, something to make sure you get an alcohol, an OH in the end. Note, this is a primary alcohol. It's a primary alcohol because I reacted with formaldehyde. Is that the only way to make a primary alcohol? No. In our previous example, we had a primary alcohol. We made it from an epoxide. But if you want to make a primary alcohol from a carbonyl, it does need to react with formaldehyde. What if you react with a different type of aldehyde, as is presented in our next example? So our next example is another Grignard, but a different one this time, with an aldehyde. Straight out of the gate, attack the carbonyl carbon. Note, Grignards are famous for making carbons appear and disappear. Make sure you have the right number of carbons in the end. This carbon right here is the carbon that was attacked. This carbon is that carbon. The carbon that was attacked should have a benzene dangling off of it. It should have an O- dangling off of it. And it should have 1, 2, 3, 4 carbons of butyl dangling off of it. This is the new bond that was made from attacking that carbonyl carbon. Then acid workup, protonate the O-. Done. Product. This is super easy. Why didn't we talk about aldehydes and ketones first? Grignards can react with ketones. The same 4-carbon Grignard, but this time adding a ketone instead. What you gonna do first? Attack the carbonyl carbon. You bet. I'm pointing in a different way this time, not to be difficult, but just because it seemed clear. This is the carbon that was attacked. This is the carbon that used to be the ketone. This carbon should have a methyl. It should have a benzene. It should now have my 4-carbon Grignard dangling off of it. Check, check. Done. All reactions of this type will have some acid workup step later to make sure you get a neutral alcohol product in the end. Did you catch that? I said neutral alcohol product. All of these reactions will give you alcohols as product. When a Grignard, or an organolithium, in fact, when a Grignard attacks an aldehyde or a ketone, you're going to get an alcohol. Looking back at our previous example, when it attacked formaldehyde, we got what kind of alcohol? Primary. When it attacked the aldehyde up top, we got a secondary alcohol. When it attacked the ketone at the bottom, we made a tertiary alcohol. So can you ever attack an aldehyde and get a tertiary alcohol? Nope. You're always going to have primary or secondary if you attacked an aldehyde, depends on whether it's formaldehyde or not. You're always going to get tertiary if you attack a ketone. Can you ever make secondary attacking a ketone? Not if you're attacking with a Grignard or organolithium. That seems pretty clear. I think I got it. So moving on to how do you synthesize something like this? I think syntheses like this students find pretty approachable. We are making an alcohol every time. So start by circling the circling the carbon that has the alcohol attached. Done. Imagine breaking any one of those bonds, any one of those carbon-carbon bonds neighboring. This one, or that one, or this one. Any of those bonds could be broken. I'm going to break off that rightmost piece. And what happened was this carbon is going to be the negatively charged carbon that did the attack of what used to be the carbonyl. So I'm telling you that that Grignard used to be, or that molecule had come from a 5-carbon Grignard molecule, and then that carbonyl compound on the left. Here's what the whole forward synthesis would look like if we wrote it out as a forward synthesis. Combine the Grignard and carbonyl, and then you must follow up with acid. The acid cannot be part of the first step with the Grignard. It's a big deal, unfortunately. Can you imagine other ways to do this very same reaction? I hope so. I hope you can imagine at least 2 more ways, and you're going to draw them out and send them to me. Let's go through a couple of other examples together. We will start out with N-octyl alcohol, octanol. That's this guy. If your memory is pretty good, we just synthesized this thing, but we synthesized it from an epoxide. But now that we know Grignards also attack carbonyls, we could envision this thing being made from a carbonyl and a Grignard reacting together. So that last slide says start out by circling the carbon that has the OH. This is if you're wanting to do a carbonyl synthesis rather than an epoxide. So circle the one that has the carbonyl. Circle the one that has the alcohol. Imagine that that used to be a carbonyl and that this carbon-carbon bond is the one that was made by the Grignard. So I could imagine this thing being synthesized from a 7 carbon Grignard. Man, it's hard to say the word 7 and not write 7. A 7 carbon Grignard and a 1 carbon carbonyl. So formaldehyde, really. That's easy enough. Are there more than one ways to propose this synthesis using a carbonyl? No. You could use an epoxide or formaldehyde and a Grignard. That's the only options for this guy. However, the next one does have more than one option. Start by circling the alcohol carbon. And you can imagine that that used to be a carbonyl. You're going to break one of the bonds on either side and turn the not alcohol side into the Grignard and turn the alcohol side into the carbonyl. So I could imagine a 2-carbon aldehyde being attacked by a 4-carbon Grignard. That's one way. I could also imagine this is the bond that was made. So I could say a 1-carbon Grignard attacked a 5-carbon aldehyde. Is there an advantage to one over the other? Not at all. Not this time. Do I want to force you to do one synthesis or another? Not typically. I want you to have options and choose what's best for you. Why might you choose one over the other? If your instructions were narrow to say, synthesize the following using alkenes of 4 carbons or fewer, something like that. This has 5 carbons. That's too much trouble to make. Choose this pathway. Something to note in all of these, and I didn't do it in the one above either, you're going to add together the Grignard and carbonyl thingy, and then you're going to add acid. And so when you're doing the synthesis, you might want to remember, you should remember, to write those details as well. One more synthesis example. This guy. What kind of alcohol is this guy? A primary, secondary, tertiary? Because he's a tertiary alcohol, that means he has to have come from a ketone. Do I want you to memorize that little fact? No, sometimes I think it's helpful if you know that to make your process faster, but nah, whatever. It's a tertiary alcohol. Can you imagine 3 separate ways to make this alcohol? I hope so. Let's draw them. Start by circling the carbon that has the OH. And you could imagine breaking any of the 3 bonds over there, around it. We're going to do this one in pink. There's my ketone and my Grignard in pink. We're going to do another one in blue. There's my Grignard, there's my ketone. We'll do the last one in green. Is there advantage of any of these over any other? No. Why might you choose one over another? Depending on your instructions of what you're allowed to do. But any of them are acceptable. All of them are acceptable. Woo woo. We won't go through it now, through examples right here now, but I think it's useful for you to remind yourself how to make alkyl halides. Why alkyl halides specifically? Because the 3 syntheses we just laid out all went backwards 1 step to show me the Grignard and carbonyl compound that could react together. But because I'm trying to be kind to you and trying to help you prepare for the final exam and the MCAT and all that mess, I want you to bring back other old reactions too. So instead of just synthesizing something from the Grignard and carbonyl, it's likely you will have to synthesize something from either starting with an alkane or starting with an alkene or starting with an alcohol or starting with an alkyl halide. Those are my 4 favorite options for what you might potentially start a synthesis with. To me, the easiest thing to do when presented with a Grignard synthesis is take it 1 step backwards to show me the Grignard and the ketone, or the Grignard and the carbonyl compound, and then figure out how to synthesize those 2 pieces from old stuff. Alkyl halides are definitely going to be part of your synthesis no matter what I tell you to start with, because every Grignard comes from an alkyl halide. So make sure you know how to make alkyl halides, and here's a reminder of how to do that. Next time, we'll talk about class 1 carbonyls, all of those carboxylic acid derivatives. Do you think they can react with Grignards and organolithiums? You bet they can. That's all.